In this video, we're going to take a look at how to calculate volume using the shell method. If you watched how to calculate volume using the disk method, you know what problem we're trying to solve. We're going to have a closed bounded region in the two-dimensional plane. We are going to create a three-dimensional object by rotating that region around either a horizontal or vertical line. When we rotate that region around a horizontal or vertical line, we create a three-dimensional object, and we are going to try to find the volume of that object. So rotate the area around some horizontal or vertical line, and then find the volume of that figure. Now, we did this using the disk method in a previous video. So now we're going to use the shell method to do this. So again, just to visualize, we have a two-dimensional area. Let's say the area under y equals x squared from x equals 0 to x equals 2. And let's say we're trying to revolve that around the x-axis. Well, if we revolve that around the x-axis, then we create this three-dimensional object here, and we want to find the value. When we dealt with the disk method, we set up rectangles like this, and then we rotated those rectangles around the x-axis, and we created disks. And we could find the volume of the figure by adding up a bunch of these disks and then letting those disks have widths go to 0. So that was the disk method. With the shell method, what I'm going to do is, instead of orienting my rectangles perpendicular to the axis that I'm going to rotate around, I'm going to orient my rectangles horizontal, or in this case, but parallel in general to the axis that we're rotating it around. So I'm going to have a rectangle like this. If I rotate that rectangle, what I end up with is a small tube, which we refer to in math as a shell. Now we're going to get a shell for each little bit that goes from all the way at the y equals 0 mark to all the way to the y equals 4 mark. We're going to get different shells, and these shells are going to have different, well, if I look at it this way, it's a distance from left to right. We're going to call that the height, because we're going to think about these basically as tubes, right? Or sections of pipe. We're going to have a bunch of those. And when I take the limit as the given rectangle, the rectangle that I use to create it, as that given rectangle has width or height that goes to 0, add them up, we're going to get the volume of the three-dimensional object. So again, we start with rectangles that look like this now, and then we're rotating them around. But the rectangles are parallel to the line I'm rotating it around. By the way, that is going to force the integration to be done with respect to y in this case, whereas with the disk method, our rectangles were the other way, and so the integration was with respect to x. Now our rectangles are going to be this way, so it's going to be done with respect to y instead of with respect to x. So that's the visual of what's happening here. We're going to cut rectangles in the region, and there's going to be a lot of rectangles. They're all going to be parallel to the line of rotation. When I rotate those rectangles, I create little tubes or shells, and I'm going to take the limit as the width of those shells goes to 0. This becomes a Riemann sum. Since this shell that we're using is a tube, that is just a cylinder with a hole cut out. So the volume of that little tube is going to be 2 times pi times the average radius, because there will be a thickness to it, times the height, and then times the thickness of the shell. The thickness of the shell is what we're going to take limit going to 0 when we sum up. And then that Riemann sum, when I take limit as thickness goes to 0, turns into an integration. So with the shell method, the volume is going to be calculated by 2 times pi times the average radius times the height integrated with respect to x or with respect to y, depending on how the tubes look. And that gives me this general formula. Volume is, if I have a horizontal axis of revolution, this shell method volume is going to be calculated by 2 pi integrated from C to D. This symbol here is called rho. It's the Greek letter rho. It's like the R in Greek for radius. So that's your average radius times the height and integrated with respect to y. Again, horizontal axis of revolution now, we're integrating with respect to y. Vertical axis of revolution, I'm integrating with respect to x. And again, it's going to be 2 pi average radius times height integrated from 0 to, not 0, from A to B. So that's the general formula for utilizing the shell method to come up with value. 2 pi radius height. Now, just so that I explain what we're talking about when I say radius and height, remember, let's again visualize this situation. My rectangle is right here in orange, but it's this little section there. As I rotate that around, the radius of my shell is going to be from the rectangle down to the line I'm rotating. So the rectangle's height, in this case, that's just a little bit over 2, down to the line I'm rotating, that's down to a y value of 0. And then the height of the cylinder is going to be the length of this rectangle. So the length of this rectangle is going to be the height of the tube. So from right to left on this tube here. So radius is from center to the top, and then the height of the cylinder is the length of this tube. And obviously, at this stage, whoops, at this point, the tube only goes from the curve up to x equals 2, but it'll have a longer length down here, but a shorter radius if I drew my rectangle down here. So what I'm saying is, at this particular value of y, the radius goes from here to the x-axis, and the height is pretty short, that we get a pretty short length of pipe or a pretty short shell. But if we move our rectangle from here to here, and then use that rectangle, you'll see that the radius on this shell is shorter. The height is longer. The height is going from, whoops, again, the curve down to x equals 2, or x equals 2 down to the curve if I want a positive numerical value. So we can see that we can get lots and lots of different shells. Obviously, we add them all up. Again, these are just two representative shells. One is a little bit shorter, but has bigger radius. This one is longer, but has shorter radius. In general, some shells are going to have short radius and be short and all that kind of stuff. But we get these types of shells, which are, again, think of pieces of pipes. So that radius, again, rho is the Greek letter that we're using, times height. Integrated from C to D and then multiply times 2 pi. Again, 2 pi because that's the distance around, and then radius gives you the radius, length, and then the thickness goes away because we're integrating with respect to y, and that with respect to y integration is where my thickness is going to go smaller and smaller and smaller until we get to 0. Let's do an example. In fact, let's do an example that we've dealt with before in our previous video when using the disk method. Let's take the volume of the object made by revolving the region bounded by y equals 4 minus x squared, x equals 0, and y equals 0 in the first quadrant around the around the y-axis, around the y-axis. We calculated this using the disk method in our other video. Now let's use the shell method to do this. So once again, I'll start out graphing this and sketching the region I'm looking at. Y equals 4 minus x squared is this parabola pointed down. Y equals 0 is the x-axis. X equals 0 is the y-axis. And we're in the first quadrant. So we're in this region here. I'll shade that in blue for right now. Now I want to rotate around the y-axis. So I'm going to rotate around the y-axis. If we did that with the disk method, our rectangles would go perpendicular to the y-axis. With the shell method, our rectangles are going to go parallel to the y-axis. So the rectangles that I'm going to be using are going to start at the curve and go down to the line y equals 0. Now, this is going to give me a height if I measure the top versus the bottom of this rectangle. Because think about rotating this around, it's going to give you a shell. The radius of the shell, on the other hand, is going to go from whatever place we're at right here down to the y-axis. So the radius is going to go this way, but the rectangle I'm using is parallel. Okay, so the height of the rectangle gives me the height of the cylinder, and the radius of the cylinder, the radius of the shell, is going to be at whatever value we're at here, at some x value, down to 0. Because I've drawn my rectangles this way, we're going to be integrating with respect to x as well. So the y-axis is a vertical line. That means I'm going to be integrating with respect to x. Okay. On my picture, the bounds for x went from 0 to 2. The height of the cylinder was the height of the rectangle. And we saw that the rectangle went from 4 minus x squared, y equals 4 minus x squared, down to y equals 0. The height of the cylinder, the height of the shell is that. The tricky part is the radius. The radius is going to be different at every value between 0 and 2. At every single value between 0 and 2, again, this is going to be our rectangle that I draw. The height of the rectangle is going to be the height of the cylinder that gets created when I rotate that around the y-axis. But we're at an arbitrary x value here. It looks like a little bit more than 1.25. And the radius of that cylinder is going to be from x equals 0 all the way out to this arbitrary value of x. Now, if I want to make this radius positive, I make it x minus 0. So x minus the line I'm rotating around, which is x equals 0. I replace rho of x with the radius. Again, the radius is x minus 0. And this becomes the calculation for value. If you'd like to make this look a little bit nicer, obviously you can. You can say x minus 0 is just x, and 4 minus x squared minus 0 is just 4 minus x squared. This is pretty easy to calculate by hand if you'd like. I don't. And the one thing I will remind people of is there is a coefficient of 2 in front of everything. So when you do your integration, don't forget that we have a 2 times pi in front of this. So after I multiply by 2, the volume of this object after I integrate is equal to 8 pi. 8 pi is about 25.13. So we just found the volume of that object utilizing the shell method. I want to point out we found the volume of that object using the disk method in a previous video, and it also came out to 8 pi. So this is good evidence that since these two match up, that we do have the correct method and we've done it correctly. However, I also want to point out that when we dealt with the disk method, since we were rotating around the y-axis, in the disk method, we had to do our integration with respect to y. With the shell method, when we revolve around the y-axis, we do our integration with respect to x. Because with the disk method, rectangles are perpendicular to the line we're rotating around. In the shell method, the rectangles we use are parallel to the line we rotate around. So we end up with 8 times pi. Let's do another. Let's say we wanted to find the volume of an object made by revolving that exact same region around the line x equals -3. I'll graph this in 2 dimensions and then we'll do the calculations. So we're going to swap revolving around the y-axis to revolving around the line x equals -3. We've graphed this region earlier, and now we're revolving around x equals -3. So we're revolving around this. Again, x equals -3 is a vertical line. So what's happening when I revolve around x equals -3 is I'd be taking these rectangles and each rectangle I revolve around x equals -3. The height of these rectangles give me the height of the cylinder, and where these rectangles are at, they're going to be at arbitrary x values between 0 and 2. So the region has x values that span between 0 and 2. So my x values are going to be between 0 and 2. And then my radius for the cylinder that I've created is going to go from whatever arbitrary x value I'm at down to -3. So that's going to be what I get when I rotate that thing around. And that's all the information that I need to set up my shell method. We have the height of the cylinder. Notice that the height is actually the exact same as in the previous case, because we're going to use the same rectangles. Also notice that the region goes from 0 to 2, just like in the last case. So we're going to use the same bounds. But now, since I'm rotating around x equals -3 instead of x equals 0, I'm going to go from x, instead of from x minus 0, I'm going to go from x to x minus -3. And that's going to be my radius. The x minus -3 will be my radius. So these bounds, the A and the B, are the bounds on the region. Again, since we're rotating around a vertical line and using the shell method, we're integrating with respect to x. The height of the cylinder is the height of the rectangle. In terms of x, the height of the rectangle goes from 4 minus x squared down to 0. That is 4 minus y equals 4 minus x squared to y equals 0. The radius now goes from arbitrary x value down to -3. Now, when I say x down to -3, that's x minus a -3, which we can just write as x plus 3. Now we are ready to integrate. And again, generally I use my calculator to do that. If you want to do this by hand, you just have to multiply out the polynomial and then it's polynomial integration. Don't forget that there's a 2 out in front of the whole thing. It's 2 pi, not just pi. So when I take into account that there's a 2 in front, I get 40 pi as my final answer. That's around 125.66. So that's approximately 125.66. That is how we do the shell method around vertical lines. Now, I want to point something out about this particular situation. In this situation, this figure is going to have a hole in the middle. There's going to be a big gap between the line we're rotating around and our region. So if I rotate that region around, I have a hole in the middle. And that's fine. We're not troubled by that. The shell method value, I can take care of those holes in the middle because I'm just telling us to use the rectangles from x equals 0 to x equals 2. I'm not using any rectangles from -3 to 0. So the shell method handles holes in the middle very well. I don't need, like we did the washer method with the disk method. Here, I don't need to have a new method to deal with a washer method or to deal with holes in the middle. The shell method does that on its own. It just says we're going to rotate each of these rectangles around and we're going to use the x values between 0 and 2. And when I do that, I'll be left with a hole in the middle, but that's just fine. Our calculations dealt with that. Again, in the last two examples, what we did is we took this region and we found the value by rotating around the y-axis If I rotate that region around the y-axis, I get this gray figure. And we actually have seen this earlier using in an earlier video when we dealt with the disk method. Okay. And we got, what was it, 8 pi, which was about 25.13 as the volume for this figure. When I rotated around the line, x equals -3, well, I'd take that region, rotate around the line. Notice we're going to get a big hole. We get this region here. And we got the volume of this figure as about 125.66. So that's what we ended up with. Again, that sort of three-dimensional figure. I've graphed it in red, but you can graph it however you like. That's the idea. So we've just calculated the volume of that type of figure. I wanted to give at least one three-dimensional visualization of this. And we did that by taking little rectangles and then rotating them around. And that rotation gives me nice tubes. The height of the rectangle is determining the height of the cylinder, the height of the shell. And then the radius goes from whatever x value we're at to wherever we're rotating it around. Now, this is with a vertical line of rotation. If we did a horizontal line of rotation, we would have to integrate with respect to y with the shell method. So let's go ahead and do that. Let's do another example. In this example, we are going to rotate around a horizontal line that is the x-axis. We will use the same region we've been using for both examples 1 and 2. And we'll take that region and rotate it around the x-axis. Same region. I won't waste a lot of time sketching that because we've sketched it a couple of times already. We want to rotate around the x-axis. If I rotate around the x-axis and I'm using the shell method, then my rectangles need to be parallel to the x-axis. So the rectangles I'm using are going to do this. The height of that rectangle is going to go from the curve down to the bottom of this region, which is x equals 0. My y-axis is x equals 0. The radius is going to do that, the radius of the shell. So the height of the shell is the height of this rectangle, and the radius of the shell, which we call rho, is going to go from an arbitrary value now on the y axis, so some arbitrary y value, down to the line I'm rotating it around, which is y equals 0. Because our rectangles are going to be horizontal, when we integrate, we're going to be integrating with respect to y. And again, that makes my radius just down from arbitrary y value down to 0. Before I move on, I do want to point out that the y values go from 0 all the way up to 4 when I look at this region. So the region has y values which will go from 0 to 4. I'm ready to find the volume using the shell method now. Well, I'm almost ready. The bounds are y bounds, so they're going to go from 0 to 4. Those are the bounds of the region. My radius is going to go from an arbitrary y value to 0. That's basically arbitrary y value down to the line y equals 0, down to the x-axis. Now I need to find my height. Now my height is going to go from the curve down to the line x equals 0, down to the y-axis. Because we're integrating with respect to y, I need to take my curve and write that as x is equal to a function of y rather than y is equal to a function of x. If I subtract y from both sides and then add x squared to both sides, I get x squared is equal to 4 minus y. Because we're in the first quadrant, I can solve for x by taking x as the positive square root of 4 minus y. So this is my equation written in terms as x is equal to a function of y. When I integrate with respect to y, it's important to do that. So now we have my height, which is x is equal to 4 minus y underneath the square root. Down to 0. And then my radius is just y. If I want to do this by hand, I can, but it's going to be a lot easier to plug in this integration into my calculator. That's what I'm going to do. Integrate from 0 to 4 of y times the square root of 4 minus y with respect to y. I've mentioned earlier that on your calculator, you can just use the variable key, and as you type it in, the variable key will show up as x's, but this integration would be the same no matter what letter I chose to put in there. So in fact, if I chose some really weird letter, like I chose the letter P, this integration would be exactly the same. If I chose to use the letter X, that would be the exact same thing as well. If I chose, the letter W, that integration would be the exact same as long as I'm integrating with respect to W. So whichever letter you choose, you're going to get out the same answer. So when you type it into your calculator, I tend to just use the variable key, and whatever the variable key gives me, I get that. I use that numerical value. Don't forget that we are integrating this with respect to y, but I have a 2 pi out front. And when I do this, I get about 17.0666726, which actually should be 17 and 1/15 times pi. My calculator doesn't give me a precise answer on that because, again, we're integrating something with a square root around 0. So it's off by just a little bit, but it's 17 and 1/15 times pi, which is about 53.62. If we're using a rounded answer, then I don't have to really worry too much about what this pops out. But if I'm trying to get an exact answer, I do have to recognize sometimes that my calculator can round it incorrectly. But there we go. This is the volume, and if you remember, this was the exact volume that we got using the disk method. So we've done this problem using the disk method as well. Using the disk method, it was just pi times radius squared, and the radius was 4 minus x squared down to 0. So the height, again, of this one. But we were integrating with respect to x when I was using the disk method. Now, when we use the shell method, since we're dealing with a horizontal line, we're integrating with respect to y. Getting the same answer either way, but just taking a different path to get that answer. Let's try example 4. If you want to try this on your own, push pause on the video. I will try this in just a couple of seconds. Example 4 asks us to find this value of the region created with y equals x squared, y equals 0, and x equals 2, rotated around the line x equals 2. I'm going to draw that out in two-dimensional space. This is another one we've done before, but I'll draw it out in two-dimensional space. Y equals x squared, y equals 0, and x equals 2 are all drawn on this grid. We are going to look at taking the region whose perimeter has all 3 of those curves, so that's this region in here. I've shaded that in blue already. And then we're rotating it around the line x equals 2. That's the line right next to the region, like adjacent to the region. So we want to rotate that region around that vertical line. If I want my rectangles to be shell method rectangles, then I'm going to set up my rectangles parallel to the line I'm rotating around. That means the height of the cylinder, which is the height of this rectangle, is going to be from the top of the curve down to the bottom. The top of this curve is y equals x squared. The bottom is y equals 0. Because my rectangles are vertical, we're going to be integrating with respect to x. In terms of the radius, now the radius is going to go from the rectangle to the line I'm rotating around. That is from an x value to the line I'm rotating around, which is x is equal to 2. Be careful with this. If I do an x minus 2, because all of my x values are under 2, if I do x minus 2, I'm going to get a negative radius. However, since 2 is bigger than all the x values I'm dealing with, if I do a 2 minus x, I'll get a positive radius. When I plug it into the shell method, it's important that I have a positive radius, or otherwise my integration comes out as negative. So that's how we do it. Rectangle height, which is the height of the cylinder, is from the curve down to y equals 0. And then the radius is from 2 down to x. I'm rotating around a vertical line, so I'm going to be integrating with respect to x using the shell method. And then since I'm integrating with respect to x, my bounds on x go from 0 all the way up to 2. Let's set that up. Volume using the shell method. My x bounds go from 0 to 2. My radius, again, if I wanted a negative radius, which I don't, I'd do x minus 2 because all of these x values between 0 and 2 are smaller than 2. I want a positive radius, so I'll do 2 minus x. The height of that rectangle, since I'm interested in integrating with respect to x, the top of that rectangle is x squared, y equals x squared. The bottom of that rectangle is y equals 0. So we're going from x squared down to 0. Integrating from 0 to 2. And then obviously I can't forget that I have a 2 pi out front. That's one thing people often do. They will forget about this 2, and so their answer will be half of the answer they should have gotten. But again, just make sure that when you're integrating, you have that in there. You have the 2 and the pi in there. That is 2 and 2/3 times pi, which is about 8.38. We did this utilizing the disk method. And with the disk method, we had to convert everything into integrating with respect to y. And it was kind of a hard problem using the disk method. With the shell method, once we get that down, it goes a lot easier. By the way, if I would have swapped out, if I'd have had x minus 2 here, my answer would have been a negative 2 and 2/3 pi, or a negative 8.38. So if your answer ever turns out to be negative using the shell method, obviously volume cannot be negative. So you probably flipped your radius start and end places. So just one last thing. Obviously, we had this region here that we were rotating around the line x equals 2. And when we do that, this is what we just found. We found the volume of this thing. Kind of looks like a witch's hat or a wizard's hat um, kind of shape, but obviously filled in. There's no holes in it. But that object, that sort of cone-shaped object, is what we just found the volume of. And we said the volume is about 8.38, or if I was being exact, 2 2/3 pi. So there we go. So this is the wizard's hat we get, but I do want to mention one thing about these cylinders. Again, this hat is created by using a bunch of cylinders or a bunch of tubes as approximations. And you can see in this picture that we're going to take a rectangle and rotate it around that line x equals -2. The height of that rectangle is the height of this tube or cylinder. And the radius goes from some arbitrary x value down to the line we're rotating it around. So this is the cylinder this is one of many cylinders that I'm using to approximate. And then I let the limit as x go to 0 make all of these cylinders get thinner and thinner and thinner. And then better and better approximations turn out that way. But again, height of the cylinder is determined by, in this case, from my curve y equals x squared down to y equals 0. And the radius is some arbitrary x value down to the line x equals 2 that I'm rotating around. Or I should say from x equals 2 down to the line arbitrary x value, because that gives me a positive. Hopefully that makes sense. And then when we approximate with lots and lots of those cylinders, it fills up this object. Once we've rotated around the line x equals 5, excuse me. So last example, we rotated around the line x equals 2. Now we can extend that to say, let's rotate around the line x equals 5. The nice thing about this is that most of the work is done for me. In fact, the only thing that's going to change, since we're using the same region, is the radius. The radius is going to change, but we're going to still have the same bounds. And the height of the cylinder, the height of the shell, is going to be the same as well. Let's start with the two-dimensional graph. So we started last example rotating around the vertical line x equals 2. Now we're just going to move that line over to x equals 5. We're going to get a big space in the middle, but remember the shell method handles spaces in the middle just fine. The heights of every single rectangle that I drew are going to be exactly the same. The only thing that's changing now is that the radius, instead of from x to 2, now we're going to go from arbitrary x value out to 5. And if I want to make that positive, since 5 is above the x values that I will be using, I need to go 5 minus x so that radius stays positive. I am going to start with our previous example and just change some things around. We're going to rotate around the line x equals 5 now. Still, that is a vertical line, so I'm integrating with respect to x. The height of each shell is still x squared minus 0, still going from the top of the curve down to y equals 0. So y equals x squared down to y equals 0. The radius has changed. Instead of going from 2 to an arbitrary x value, now we're going from 5 to an arbitrary x value. My region still has x value bounds from 0 to 2. So that's all I need to do there. Obviously, these numbers are going to change. When I integrate with respect to x, recalling that I need to multiply by 2 pi, I end up getting 18 and 2/3 times pi as my final answer, which as a rounded version is about 58.64. This would be in cubic units because we're doing with volume, but I know I haven't mentioned that before, but we're dealing with cubic units now because it is a volume. So it's a very short step to say, well, if I've already rotated this region around one vertical line, then I can just adjust my radius and rotate around any other vertical line by just adjusting the radius. Again, that was the last example we did. And now I just change that, change the radius. Now, pictorially, why this is true, why we don't have to adjust the height, is because in the last problem, as you saw, we had these cylinders whose heights were determined by the curve to the x-axis, and they were rotated around the line x equals 2. But now if I rotate that same rectangle around the line x equals 5, I'm just getting a larger cylinder in terms of radius, but the heights of these cylinders are exactly the same. And I'm going to take cylinders all the way from 0, x equals 0 to x equals 2 in order to get the total volume of the figure when I rotate around that line. By the way, the figure that I'm getting is going to be this one in purple. It's going to have, it's going to have a big hole in the center. But you can see how this region in 2 dimensions has been revolved around the line x equals 5. And that little orange strip, that is just one of many shells I use to approximate. So again, heights of the things were the same, but now, again, we're rotating around a different line. So we get that picture, and the volume of that object we just saw is about 58.64 around this purple object there. Now we may ask, why do we need a new method for value? Well, it turns out having the disk method and the shell method is pretty necessary because of the way they interact. When I rotate around a horizontal line, In the disk method, I integrate with respect to x. In the shell method, I integrate with respect to y. That's the reverse if I rotate around a vertical line. So if I have an equation which is really hard to solve for x or really hard to solve for y, but easy to solve for the other one, then I can use the method where I integrate with the nicer integration. Whether I like to integrate with respect to x or integrate with respect to y, I can use the easier of the two options. This is an example where, example 6 is an example where we need the shell method in order for this to work. We want to find the volume of the object made by revolving the region bounded by y equals x to the third plus x plus 1, x equals 1, and y equals 2 around the line x equals 2. So we want to revolve that region around a vertical line, that vertical line being x equals 2. Well, if I tried to use the disk method, I'd have to integrate with respect to y. And if I tried to solve this equation where I ended up with an x is equal to a function of y, it would be very, very difficult. So I don't want to use the disk method because I'd have to integrate with respect to y. But the shell method works just fine because integrating with respect to x, I can use directly the x to the third plus x plus 1 as my value. Let's graph this and then do the problem. Okay, so I've graphed these three curves, these three, the two lines and the one x to the third plus x plus 1 curve. When I do that, we see that the region right here is the only closed bounded one. So this little almost triangular shaped region is what we're looking at. This one I've colored in blue. I want to revolve that around the line x equals 2. Now, in order to do that, I need to figure out my rectangles. So since I'm going to use the shell method, my rectangles are going to be parallel to the line I'm rotating around. They're going to be vertical. My radius is going to go from x equals 2 to some arbitrary x value. So my radius is going to be here from 2 to some arbitrary x value. So 2 minus x will be my radius. The height of this rectangle is going to go from my curve, y equals x to the third plus x plus 1, down to y equals 2. Here we had y equals 2 as this line. Now, the other part about this is I need to find the bounds. In this case, this is one of those tricky cases because these 2 points are really nice to find. This point is not a nice one. This point, we would probably have to rely on using my calculator to find the intersection of this x to the third plus x plus 1, y equals x to the third plus x plus 1, and y equals 2. But that's all right. We know how to do that. Um, we've seen how to do that. If I find the intersection with my TI 84 calculator, I get a little bit better decimal expansion than just this 0.68233, but it's not a very nice value for my X value. But that's okay. Again, if I'm okay with approximate answers, I can just use an approximate decimal to start this out with. And so I'll use that approximate decimal that my calculator gives to start this X value out with. Now I am ready to integrate. So my radius, like we said, 2 down to some arbitrary X value. The height of the cylinder, which is the height of that rectangle I drew, is going to go from x to the third plus x plus 1 down to y equals 2. Again, top of the rectangle to the bottom of the rectangle. Top of the rectangle was x to the third plus x plus 1. Bottom of the rectangle was y equals 2. And then the bounds, I get one of them was an x value, my lower bound, my left-hand x value was 0.6823278 if I found it on my calculator. The other bound was x value of 1. Again, if I'm looking for an approximate answer, this is not a problem. If I'm just looking for my answer rounded to a couple of decimal places. If I was looking for an exact answer, I'd have to solve this algebraically and figure out what that number is actually. But for my courses, generally speaking, approximate answers rounded to a couple of decimal places are just fine. So I type that in to my calculator. It takes me a minute to type that in, but that's fine. It's a lot less than doing everything by hand. And I end up with just a little bit over 1 if I round to 2 decimal places. So if I round to 2 decimal places, I get just over 1 as my answer, 1.01. That is after I've multiplied by 2 pi, by the way. So that is my final answer after I've multiplied by 2 pi. Hopefully all of that makes sense. This shows you that because I couldn't solve for x here, that the shell method is necessary because there's no way I would be integrating with respect to y this type of a function. I couldn't deal with that type of a function with integration with respect to y. And also on the other side, with the disk method, there would be functions and lines of rotation. If I rotated this same region around the line y equals 0, then I need to use the disk method because the shell method would require me to integrate with respect to y because that's a horizontal line. So both the disk and the shell method are necessary four tough looking functions, functions where I don't easily solve, where I can't easily solve for y or for x. Let's do one more example. This is the example of what we call a torus. Now, we want to find the volume of an object made by revolving the inner region of the circle x squared plus y squared equals 9 around the line x equals 6. So the region here we're looking at is the inside of a circle of radius 3, which is centered at the origin. And we want to rotate that circle around the line x equals 6. This is the first one where we don't have our equation solved for y. And we'll see how this one works out. When I graph this, we have the circle and the line. And I'm looking at the inside of that circle, so the shaded circle in blue, and this line. And I want to take that all the way around, okay? So it's going to look kind of like a donut. It's going to be circular shaped, and it's going to be looking like one big long tube that comes around and basically connects to itself. So you can think of this as a donut or like a hula hoop. That would give you an idea of what that is. And that object that we create is called a torus. You'll notice that this is a vertical line, so we are going to be integrating with respect to x if we use the shell method, which it's better to use the shell method on this one. When we look at the bounds in the x values go from -3 to +3. And then anywhere between there, we're going to have arbitrary x values, and we're going to have a bunch of little rectangles that are creating our cylinders. The rectangle is going to go from the top half of the circle down to the bottom half of our circle. That's going to be important when we set up our integration, because what we're going to have to do is we're going to have to solve for y. And the top half of our circle represents positive y values. The bottom half of our circle represents negative y values. So when we go from the top half to the bottom half, we're going to go from positive y values down to the negative of that same y value. And then our x values range from -3 to 3. The radius that we're going to create with the cylinder is going to go from x equals 6 down to whatever arbitrary x value we're at over there. So from 6 down to the arbitrary x value. And then, like I said, the height of this rectangle, which is the height of the cylinder we create, is going to be top half of the circle to bottom half of the circle. I now have everything that I need in order to do this problem. Okay, the bounds I know are going to go from -3, x values of -3 to x value of +3. The radius, the 6 is the bigger number compared to the arbitrary x's that we're going to use. So we go 6 minus x as the radius if I want it to be positive. If I did x minus 6, I just get the negative of the answer that I want. And then the height goes from the top of the circle to the bottom of the circle. Over to the side, let me just explain what that is going to mean algebraically? When I try to solve for y, the first step would be subtracting 8x squared from both sides. Now, the next step would be a square root. Because the circle is the way it is, if I took a positive square root of this 9 minus x squared, this equation would give me the top half of the circle because the top half of the circle represents positive y values. On the other hand, if I took a negative square root, then that would indicate that my y values are negative, and that would be the bottom half of the circle. So when we talk about the height of the cylinder or the height of the rectangle that I drew, it's going to go from the top half, which is the square root of 9 minus x squared, down to the bottom half, which is the negative of the square root of 9 minus x squared. A lot of times, instead of doing a minus and negative, I will just do a plus. And you'll notice that when I have the square root plus another copy of that square root, I just get two of those square roots. In other words, if I wanted to rewrite this and make it a little bit easier to type into my calculator, I would say, well, the square root of 9 minus x squared plus another copy of 9 minus x squared under the square root is two copies of 9 minus x squared under a square root. That's probably what I would plug in into my calculator. I will give you the exact answer in just a moment. But right now, let's just plug this into the calculator. 2 pi integration from -3 to 3. Make sure the 6 minus x is in parentheses so that the entirety of 6 minus x gets multiplied by this whole thing and not just the x. By the way, this is actually something you could do by hand if you wanted. We have the techniques to do this by hand if you'd actually like. When I hit enter into my calculator, I get approximately 1065.92. Which, interestingly enough, is about 108 times pi squared. So the pi is being squared. The 108 is not being squared. Okay. So the torus has volume of, this torus has volume of 108 times pi squared. That's the torus of, we get with circle of radius 3 rotated around the line x equals 6. So that is the way we get that. Okay. Let's look at a picture of that torus. All right, so we're looking at a torus, and obviously I don't expect you to be able to graph these on your own or anything, but you should be able to graph in 2 dimensions what's going on. But I just wanted to show you the picture of this. So we have circle centered at the origin, radius 3. We're going to rotate that around the line x equals 6. And we end up getting a figure that looks like this. Like I said, it looks like a donut or an inner tube or a hula hoop of some shape. That shape is called a torus. It's well known in mathematics. And you can see why the you would have two pies around. We have the pie that's from the original circle, and then the pie that you get that when you essentially circle this way. So the cross section of this thing is a circle, and as we rotate it, we get a circle as well. And that's why we end up with pi squared. In this case, it was 108 pi squared. There is a general formula for the volume of a torus as well. You can look that up at some place if you'd like. By the way, in general, why we're getting this is you take the area of the inner circle, which is pi r squared, and you multiply it times 2 pi times the radius of this circle, which will be 6. So anyways, in this case, it would be pi, well, let me do this, pi r squared, and then multiplied times the circumference of your travel, which is 2 times pi times a different radius. In my example, that would have been pi times 3 squared multiplied times 2 pi times 6. Let's see if that works out. Take 3 squared times 2 times 6. And sure enough, you get 108 times pi squared, which is exactly what we got here. So there is a general formula for the volume of a torus. And again, it's pi r squared. That's the area of the circle that we start with. And then essentially the circumference of travel as we rotate it around, which is 2 pi times the other radius. So there we go. In any case, I don't expect you to know the formula for the volume of a torus, but you should be able to set something like this up, get an approximate volume, get an exact volume if you want, but get an approximate volume, and then you're off to the races. All right, as long as you can do the shell method to find value, then you're good to go in this section. So to wrap this up, we've seen a lot of different examples where we found the value of an object created by rotating a region around a horizontal or a vertical line using the shell method. In the previous video, we used the disk method, and we can see that both are necessary because sometimes it's hard to integrate with respect to y. Sometimes it's hard to integrate with respect to x. So that is the idea of the shell method and how we use the shell method.